Okay, so good morning, everyone. So all our recent lectures have been formal in the sense that we are doing abstract. Abstract meaning, lots of ideas. Okay, so I tried to use the assignments, the problem sets, to make you do concrete. Okay, so I could have done this in the second half of the course while I was doing something, much more tangible than simple calculations. But those will be material mostly that you have seen in some form of the other in earlier courses, but will be taught at a much higher level because it's an MSc level course. And so I don't know, it's my style maybe, and so it is abstract, so you have to bear with me for maybe one lecture or two more lectures, but after which we will be doing really straight ahead applications of classical mechanics, but this is more like the formalism of classical mechanics. Okay, and do not for a moment think that just because it's abstract it means it's useless. That's not true. Okay, so this is more a way of defending the way I've been approaching the course, and I've been also observing that in the last couple of lectures that the student response has not been particularly great, and that usually indicates that there is an issue, and the floor is open for some comments. No comments? Okay, so we studied canonical transformations in the last couple of lectures. Okay, and can we use this for something? So an ideal situation would be that we find new coordinates. Okay, so what I have in mind is we have Qi, Pi, and Hamiltonian, which is a function of Q's, P's, and even possibly time dependent. And then you make a canonical transformation to, say, capital Qi, capital Pi, and a new Hamiltonian, which I call H prime, and such that it is only a function of capital P and T. Okay, that means so in the new coordinates, okay, so what happens if all coordinates are cyclic?
Sir, do you mean H prime of P, Q?
No. It can have time dependence, maybe, but it does not have any dependence on Q, on capital Q. So H prime would have been, okay, so that's what I'm saying. If coordinates don't appear, they are cyclic, right? So the corresponding, okay, so in the new coordinates, it's not a question, I won't give a question. new coordinates such that, you know, say that. I'm not saying if you, so you have to find some canonical transformation such that your H prime, the new Hamiltonian, does not have any coordinate dependence. That's what I mean. Is that clear?
Yes, sir.
Okay. So if they are cyclic, that means the pi, so pi dot would be dH prime, there's a minus sign, right? Minus dH prime by d capital Qi. Right? That's what is the equation of motion, and this is equal to 0. And so pi's at t is equal to pi at 0. This is what we will get. Okay, and q dot, okay, is equal to dH prime by dpi, and this will be some, so h is only a function of p's, okay, so this will be some omega, okay, so let's, yeah, it would be some omega I, which is a function of all the p's and t. This is what we will get. A nice simplification happens if H prime is independent of time, then Qi dot becomes H prime, dH prime by dPj. Okay, and that will be some omega I of just function of all the p's. Okay, this is now, and what do we know from the p's? P's are constants, right? So this is very easy to integrate. What is the integration? What is Qi of t?
So omega I times t
plus some constant of
plus
integral.
some constant, yeah. So in the previous line, should that be del h prime over del pi?
Yes. Okay, so this is the ideal world where we are able to solve it and we get some very, very simple equations. Okay, so this is what you get. This is a constant. So we are done. Okay, so this is the ideal world. So so in general, this we cannot, I mean, carry these things out. Okay, so let us go to a, so let us try to see how we could get to something like this. So let us try the following. Okay, so the following is what I want to do. I want to make a canonical transformation. So let us, so if you remember, for any canonical transformation, okay, with some generating function. I'm not saying which f, it could be 1, 2, 3, 4. We saw that h prime was equal to h plus df by dt, right? Is this correct? Okay, so let us take the case of f2. So I can write two more equations. So f2, if you remember, was a function of the little q's and the capital P's. Correct? Okay, so let's do this. And so what about, so what we get is Pi is dF2 by dQi, and capital Qi is minus dF2 by dPi, right? These were the equations for F2, for the F2 case. Of course, H prime is supposed to be a function of this thing. So now let us assume that, let us try to construct. And so I'm heading towards what we wanted here, but I'll do it in a particular fashion. We'll construct an F2 such that, okay, such that, what is such that? Such that H prime is itself 0, which is even stronger than this thing. Okay, if H prime is 0, okay, if H prime is 0, then what do we get? Then we get the following. We get that both Qi dot, which is dH by this thing, is 0, and Pi dot, this is correct, this is what I want. Okay, yeah, and Pi dot is also 0. So this is very, very strong. Okay, so let us do something like this. Let us ask, so this is stronger than what we saw earlier. But for a moment, let us just say that we're looking for this F2, right? And we are able to. So now we want to ask what is what is the equation for F2? Okay. So what is the equation? So let's. So that is nothing but it's H prime equal to 0. What that implies is that H of Q and P. Okay. So, but what is P? From this equation, what we get is P is this thing, right? So I substitute that. TF2 plus okay, and it is a function of PIs. And so what we are going, so the PIs are, it could also have time dependence. So let's so put that also back in. Okay, I didn't write the argument of F2 here. It's messier. This should be equal to 0. This is an equation. Okay, notice that F2 appears inside the argument of this thing. Okay, and also it appears out here. Okay, so now, so this equation, so it's F2 is, okay, so remark here, F2 is a function of Pi as well, but for us, there'll be, okay, and but since H prime is 0, Pi dot is a constant, okay, so, but for us, they are constants. Okay, of integration. So I would explain this. Okay, so this equation star is called the Hamilton-Jacobi equation. Okay, what is it? It's a partial differential equation. In n plus 1 variables. N is degrees of freedom. What are the variables? Q1, U2, Un, and T. Okay. So how many constants? So when you integrate partial of every, so we need to do how many integrations? Roughly. All first order, right?
N plus 1.
N plus 1. Okay. So it implies there are n plus 1 integrations. And hence n plus 1 constants, integration constants. Okay. So how many PIs do we have? So we said all the PIs, we should think of them as coming through some constants of motion. So now the question to you is, how many PIs are there?
N.
N, exactly. So but there seems to be one extra constant. So we're getting, okay, so n of them can be identified with PI. Okay. I'm not saying that every integration constant is exactly PI, or maybe we could be clever, we will choose that as our PIs, right? I mean, we could do that. Okay. So that's what we will do. Okay. So now where is the extra thing? And you just come back and look at the Hamilton-Jacobi equation. Hamilton-Jacobi equation only does not involve F2 directly. Okay. One second. Apologies. I mean, my phone rang. I just put it away. I forgot to do that. Okay. So what's happening is that only derivatives are this thing. So you can see that F2 and F2 plus any constant are the same. Both solved. Star. Equation star, I mean, not star. Right? So this is the extra constant. Okay, which we ignore. Ignore for now. Okay, so you can see, right, if I add a constant, it doesn't matter to all these guys, it will just go away. Okay, so now you can see that so now we got our counts also right. We have exactly as many integration constants as I mean free things as the number of p's. So we are in business. Okay, I'll pause here for questions. Okay, so no questions. So we'll give a solution now. I'm putting solution in quotes because you will understand why. Okay, so we will go on a slight regression and create something which we will show.
Sir, can you explain why it is n plus 1 integrations?
Because there is also time, no? There are n plus 1 partial derivatives. here, n derivatives in the q's, and 1 from this.
Okay, thank you.
It's not very deep. Any other question? Okay, so the degradation is as follows. So let's go back to the standard action. Okay, this is the usual action. Okay, so in the Lagrangian picture, we fixed both q at t1 and q at t2, right? So delta of that would be 0. Okay, but now what we're going to do is we're going to do something different. We will take the same action, but we don't fix qi of t2. Okay, so once we do that thing, then you can see that S will now be a function, and we'll just so we'll just call this qi, which is definition now. Okay, I won't keep saying qi of t2. So this is a function of qi now. Okay, is this clear? Because we have not fixed it. So if I change, so I have the freedom to change the final point, and that freedom I'm calling it to be qi. Okay, we can also be a little bit more this thing. We can even sort of let change it. We can think of t2 as some final time. So what's happening here is that if this is phase space, okay, and okay, so so this is the initial point. So this is at t1. So what we are doing is we are looking at all trajectories which originate like this and go on. Okay, we are not particular, and remember, it's not like even momentum has been fixed. Okay, but any trajectory. So really, even if you think of it as an initial value problem, we have to specify some momentum, right? We have to specify some more initial conditions. So really, from that, so in this thing, we have only so if you pick a point. So actually, it's not even a point; it's a set of points, because only we have fixed the q's. The p's are not fixed. So it's some, right? Is this clear? So this is what is happening. Okay, and so now if we do variation, okay, so delta S, okay, will get one term which would be pi or dl by dqi dot delta qi at t2. But I am not going to put this t2 here. Okay, I'll put it here. Right? So this is what we get. Okay. Plus, of course, the equation of motion. So the other part would be, so let me write that also, sorry. Right? So this is the surface term. Okay. So is this clear what I have done? I'm doing the usual variation. So this being 0, is this equal to 0 is equation of motion. Is this clear? Okay. So this is what we get. So this on equations of motion. So we get delta S equal to, with equations of motion being assumed, it's just Pi. Of course, summation over I am not writing. Hopefully you delta Qi. Okay, and we can also think of T2, like I said. So if you look at this thing, so you can just write that ds by dt2 I won't write, I'll call T2 is T. Okay, ds by dt is just L. Okay, standard thing from this thing. So maybe I should call it L T dt prime for this integration and call T2 as T. And then you have this. Let's combine these two. Okay. So ds, now what we are doing here, so let me actually do this here also. I'll write this as S as a function of the Qi's and maybe even T2. Okay, so this is what it is. So ds by dt will get two variations. So ds by dt is the partial derivative, which is if there is some, if you're varying the time of those guys, plus ds by dqi qi dot. Okay, and now we can use this. So on trajectories. So what we have in mind is each one of these is a real trajectory. It's not some random thing. So on a trajectory, so we can, what is ds? So this we can equally say that ds by dqi is pi. Okay, so this. Okay, so we can rearrange things. Okay, and this is L. So what we get is ds by dt. Okay, plus we'll take it to the other side. Pi qi dot minus okay, this is clear. This is what we have, and this quantity is just the usual Jacobi, the Legendre transform, or okay, this is clear. So we got something interesting going on out here, and what I want to actually say is that okay, just give me a second. So I want to still massage it. So what I want to, let me tell you the punchline. The punchline here is that we will see that F2, okay. So yeah, let's look at this, okay. So let's, compare now this with star. Okay. So what can we say F2 should be? Okay, S. Okay, so that's all. Okay, so now we see S as a function of Qi and T okay, solves the Hamilton-Jacobi equation. Okay, of course, we also have this condition that ds, okay, we also have ds by dqi is pi, which is exactly what F2 satisfied. Okay, so that's okay. So one uses the symbol is S for F2. Okay, is this clear? So we have actually solved we have got this action, and so we are in good shape. So let's now ask something. So conclusion is, and please, this S is overused, right? S, which we use in Lagrangian mechanics, is not exactly equal to this, because we are doing something different here. We are making S into a function of the endpoints and the end time. Okay, so that's important. Okay, conclusion is that S is the appropriate generating function. Okay, so okay, so let us do an example now. Okay, we'll take really simple example, simple harmonic oscillator, where the Hamiltonian is just p square upon 2m plus half m omega square q square. Okay, and so now okay, so P okay, so let's look at the case. So here's an example. There is no, that's an extra feature, no explicit time dependence in H. Okay, so then that is actually, let's come back to, so what we have, so we have ds by dt plus h of qi. I am doing the general case now, and pi is just ds by dqi equal to 0. Okay, so now we can see here that only so S can have this guy has no time. We can solve for what I'm trying to say here is that if S okay, let S be the following, be a constant, so let's call this constant alpha 1, okay, plus some other function w of only the q's times t plus some functions only of the q's. Okay, so what do we get from here? We get ds by dt is equal to alpha 1, which is the constant, so I can put it in there. Okay, so then we get alpha 1 plus h qi ds by dqi. But now what is ds by dqi? That is just dw by dqi, because this term drops out. Only time dependence is there, so we get this kind of equation. So dw by, okay, so this alpha 1, okay, so alpha 1 can be thought of as energy. And we know that it's a constant of motion. Indeed, a constant of motion. Okay, so now we are down to having to solve. So we have to solve this equation for this. So back to our example. Okay, so we get alpha 1 plus h, which is h of q1, which is half m omega q square, plus p square, which is dw by dq whole square 1 by 2m equal to 0. Maybe I'll put a minus sign if you don't mind, because I want, or I want to take it to the right hand side, that's all. Okay, so now we can solve, we can integrate this. So dw, it's actually only one variable, so I can write it as dw by dq is equal to plus or minus square root of dw by d5 equal to, yeah, it's a standard thing, so it's alpha 2 m alpha 1 minus 2 goes off, so m square which we can integrate. Okay, so we can integrate this. Okay, so how does that work? Okay, and S will be just W minus alpha T. Okay, so now that we are done, we want to, so we have actually, in this example, in fact, we can probably even carry out the integration here. Okay, so but are we done here? So I mean the point here is, well, so alpha is our constant of motion. It's an integration constant out here, and so now we need to work out. So what is the new coordinate, right? We need to know that also, right? If we take alpha to be our this thing, so what was the, if you remember, what was the qi? So q should be df2, right, minus df2 by dp, right? So in this case, so this is just minus ds by, and I'm just taking alpha to be my this thing, right? So you can just so let's do that. And so if you did that, so let me actually, yeah, then q becomes some formal integral what am I writing? dw dq. Oh, yeah. We could do this integration minus alpha. Sorry, I'm a little confused. What was I doing? I did dw by dq. I got this, so I have to just substitute here. So minus minus t. Okay. So exercises show that q works out to be. I need my glasses to read the answer, because we can, like I said, we can do this integration. So okay, which you can write it in a slightly better way as q equal to okay. So what we can see here is this is something we knew, right? The harmonic oscillator, we know exactly how to solve. It's just a sine, so the amplitude is one variable and the phase is the other variable. So we can see that this q, so q is the phase of the oscillator. It's an angle. Okay, and we can also check what is P. P is ds by dq, and which is equal to dw by dq. And if you just work through it, we just get the usual 2m alpha minus m omega square. And if you plug in what q is, you will get your usual cosine, I guess. Okay, so the thing is that so for systems with 1 degrees of freedom, and a time independent Hamiltonian, okay, we can formally solve the Hamilton-Jacobi equation and express S as W minus alpha t, and W will be some integral of so we computed these things, right? So we just did this, right? dw by dq. So we can actually and we can express this. Even though I'm writing it, it looks like chicken and egg, but actually this you can solve by writing solve for using h equal to alpha. Okay, so we can do this thing. The story is not so simple in higher dimensions. Okay, so even if you take 2 degrees of freedom, we need, okay, so for 2 degrees of freedom, we need, even if we need one more integration constant. Okay, this may or may not happen. Okay, so there are situations where, you know, for instance, if you have, you know, some kind of rotational symmetry or whatever, rotational symmetry, we know that, and there we get a new constant. Okay, except the question is, will it be one of these alphas? What is the correct thing? Okay, so next lecture, we will discuss ideas like the following things. We'll discuss what is called action angle variables, which will be a slight variation of what we did today, and integrability. Okay, what it means. Okay, what is integrability? Integrability roughly means that, you know, we had a wish list in the beginning of this lecture where we said that, look, we would like to go to these new variables, capital Q's and P's, such that, you know, the P's are constants and the Hamiltonian is not 0, but it's some h of I or something like that. Okay, so we will do that in the next lecture. And that should actually conclude the formal part of our course, and after which we'll go on to do other applications. And I'm trying to get a guest lecture on chaos and dynamical systems with a much more general perspective. And that depends on if the person is free. So I'll update you. It will be either tomorrow or Monday if that happens. Okay, otherwise I'll continue my lectures. So I'm done for today. Any questions, comments?
Can you go back to when you took variation of S with respect to Q?
Very early, right? The beginning of the digression.
Yeah. So,
yeah.
When we say that we are on equation of motion trajectory, so isn't that when delta S itself vanishes? Because
No. Delta S vanishes only if you put delta Q at T2 and delta Q at T10. We have said delta of Q at T2 is non-zero. That is why we have delta S is this. It's not 0. See here. So what is delta Qi? It was delta Qi at T2. If we set that equal to 0, it is delta S equal to 0. Here we are not doing that. We have only fixed the initial value of the position. We have not set anything. So that does not uniquely fix the trajectory at all. Okay. So this is not, so the S is the same symbol we are using, but the S here is a function of the final point. Okay. Yeah. Any other